So here's a title of my talk. Thank you, Chairman, and thank you, Ken, and others for organizing this wonderful meeting. I want to start with a metaphor. So who have been to Din Tai Fung already? The soup dumpling shop, famous one. Oh, actually, many of them. The second question is, do you know how many soup dumpling shops in Taipei? Yeah, there's 3, right? There's only 3, right? So only 3. So you might think the dumpling formation rate of Taipei may be very, very low. But that is because you're using optical detector, your eye. If you use correct wavelengths, there's something called obscured dumpling. And even there's an obscured active galactic dumpling, something like that. So it is important to correctly estimate the dumpling formation rate in Taipei. It's very important to correct all of these. Actually, if you count everything, there are 361 dumpling shops, more than this is lower limit in Taipei. So that's what I bet even Taiwanese people have been to make all of these. So that's what I'm going to talk about today. So I'm going to, of course I'm not going to talk about dumpling. I want to review the obscured star formation and an obscured AGN in using this Akari infrared telescope. And I want to thank my collaborators. So I listed, this is a collaboration of many people in my team, in Akari team. So I mentioned here, and particularly I want to thank my team members. So these are 2 postdocs working with me at NTHU. They are very, very good. Particularly Tetsuya is sitting there. He submitted 3 papers to Nature during the last 2 years, except all of them are rejected. He's very good. And also my students are also hardworking. This is actually not my student, but this is my student. So these people, my talk is based on hard work of these people. There are some undergrad students, and this is not my student, but this is my student. Okay, so let's start talk. So the scientific motivation is we want to review the cosmic star formation history and the black hole accretion history in 13.8 giga-years of the history of the universe, when and where universe created stars and then black holes. That's something we want to review. But if you depend on optical telescope from the ground, then you're missing obscure part of the star formation history. So you only get the lower limit. So how do we measure the obscure star formation? So our answer is Akari Space Infrared Telescope. So we build this infrared telescope, and the infrared telescope need to be space. So that's why we launched the telescope to the space. So that's the launch movie. And then Akari Space Telescope did 2 large surveys. One is the all sky survey, so it's in sun-synchronous orbit. So observe the whole sky like this. And at the same time, in polar regions, we have a deep field. First, I talk about result from deep field. So this is the data, mid-infrared data in the Akari NEP deep field. One of the unique features of this telescope it has continuous 9-band mid-infrared filters. So from 2 micron to 24 micron, Akari's filters continuously covers this mid-infrared range without any gap. If you compare with Spitzer wide, in case of Spitzer, there's a wide gap between 8 micron and 24 micron. And if your feature you're looking for is supposed to be in this wavelength range, then you have to use a model-based interpretation to estimate what's going on here. That was the largest uncertainty in Spitzer-based work. Akari doesn't have that uncertainty because one of the filters can cover in this wavelength range. Okay. Then we use this data, and then we previously already published some cosmic star formation history based on this data, but however, we had a big problem. Not all Akari data were used for our work. What I mean is Akari's deep data in NAB field covers already exist in this large area of 5.4 square degrees. However, we are only using this small area of the data because we only had deep optical imaging here. So that was a major obstacle. We are sort of wasting a space telescope-based data here. So that's why we suffered from cosmic variance, and it was a problem. But recently, Subaru telescope has new hypersprang camera, which have much larger field of view. And recently, we successfully covered with this only 4 pointings, covered almost entire Akari NAB field of 5.4 square degrees. Okay. So now we can use the whole Akari NAB field data. And the young people, some of them are sitting here, did hard working of the data reducing and observation, and then we have now deep optical data over Akari's 5 square degrees field. The G-band depth is 27.5, so it's very deep. And then one of my students, Subaru's HSC doesn't have U-band capability, but U-band is also important. So one of my students took Share for HD data thanks to Academia Sinica support for Share for HD. And then he reduced the data in U-band, which covers almost the same field. And then one of my students, Simon, did the photo G calculation. So his photo G is here. Here it's very good. Delta G over 1 plus Z is 0.049, so it's reasonably good. So now we have optical data for the entire Akari field. So we can create the luminosity function. I skipped the method, but this is a summary of the method. And I jump onto the result. First, I show you the 8 micron luminosity function with this new HSC data. 8 micron is here. It's the wavelengths dominated by so-called PAH emission. So it's a sensitive indicator of the star formation activity. So it's good. And then one of the unique features here, still unique, is Akari has unique continuous 9-band filters in mid-infrared. So whatever redshift zero galaxy falls on, one of the filters can directly measure the 8 micron luminosity of the galaxy. For example, if galaxy is 0.3, then 11 micron filter can measure the 8 micron. If 0.7, then it's going to be 15 micron. If it's 1.25, it's 18 micron. It's redshift 2, it's 24 micron filter. So we don't need a model-based extrapolation like Spitzer people needed to do. And that was the largest uncertainty. So here's the resulting 8 micron luminosity function. You see from low redshift, that's 0.4, 0.8, and then 1. You see a steady and then strong, steady evolution to the higher and higher redshift. Okay. Now next, I'll show the 12 micron luminosity function. So 12 micron is a little bit off from this complicated PAH region. So this is you get the continuum of the mid-infrared emission, mid-infrared dust. And this is also still sensitive to star formation activity, so another good wavelength. Unlike in case of 8 micron, because of the continuous filters, one of the filters can capture 12 micron wavelengths at any redshift. So that was the largest advantage over Spitzer or White's. And this is resulting in 12 micron luminosity function. Again, from low redshift to high redshift, you see a steady increase of your infrared luminosity function towards higher redshift. Okay. Then last, I show you the total infrared luminosity function. To measure total infrared luminosity, even though we have 9 bands, we still need to use the SAD fitting. But if you have 9 bands, then that helps to do SAD fitting rather than you have 4 or 5 bands in this wavelength. Okay, then we estimate this infrared luminosity for individual galaxies, and then this is the luminosity function we get. And again, it's the same thing. If you, from low redshift to high redshift, you see a steady increase of luminosity function towards higher redshift. Okay, so that is the result from the Akari's NEB deep field, but Akari can do more. So these days, as Ken summarized in the meeting, future big telescopes such as JWST or TMT or GMT, they are all trying to push this to higher redshift to the cosmic star formation history. However, what we want to so those big telescopes in the near future are all trying to measure here, at higher and higher redshift. But since what we want to understand is evolution, so we want to see the difference between low Z and high Z. So in addition to measuring higher redshift, that's obviously important, but it is also important to measure a low redshift benchmark very, very accurately to study the evolution accurately. And this is where Akari's all-sky survey can do a very good job. So next, I will introduce this paper I wrote with my previous postdoc, AJ, here. Okay. And then in this low redshift work, there was a monster paper, this Sanders et al. 03. This paper, everybody cites this paper, and this paper is cited more than 1,000 times by now. But this paper is based on IRAS data, which is a satellite from more than 20 years ago. It's almost 30 years ago. And then Akari can do better in these 2 points, which are mentioned now. One is availability of 160 micron filter, which Akari has. So when you do the SLD fitting of individual galaxies, if you only had IRAS, the longest wavelength was 100 micron. So you only have data up to here. And if your data stops at 100 micron, you don't never know if the galaxy's SED is going to continue rising or it turns over. And this is a big uncertainty. But Akari covers 140 micron and 160 micron, Akari's all-sky survey. So now, for the first time, we can capture the peak of the dust emission, and then we can accurately measure the turnover, and this is critically important to measure the infrared luminosity of individual galaxies very accurately. And then Akari measured 160 micron for the whole sky. And Akari is actually the only satellite which measured 160 micron in all sky. The second point is Dave Sanders only used 600 galaxies. That's a very small sample nowadays standard. And then with Akari, we increase the sample size to 15,000 galaxies. What we did is, so Akari has 15,000 infrared galaxies, and we matched with SDSS and WISE. WISE also has mid-infrared, so then 6DF and a two-mass redshift survey, and then we collected spectroscopic galaxies of 15,000 galaxies. Okay. So one Dave Sanders is already powerful, but our sample is 20 times larger. Imagine the 20 Dave Sanders. That's scary, right? Okay. Okay. So now method is the same. I won't talk about details, but we have spec Z, so SED fit, and the Bmax for completing correction, and then measure the luminosity function. So the now question is, this monster paper, Sanders et al. 03, was correct or not? We have advantage of 160 micron, sample size much larger. So let's see. So this is the result. So if you compare, so our result here is black. Okay. And if you compare, for example, with my previous work with red, then the new data are much more smoother, stable, much smaller errors. But unfortunately, or fortunately, this agrees very well with this Sanders et al. Data. It's right on top of each other. So, unfortunately or fortunately, Dave Sanders et al. Paper was correct. But nevertheless, I think it is very important to measure it more accurately. That's what I did. Okay, now, what about star formation, cosmic star formation history? I was talking about the cosmic star formation history, but I was showing you infrared luminosity function. Now we have infrared luminosity function, so we multiply by luminosity and integrate luminosity function, then you get infrared luminosity density, which is directly connected to the star formation rate density through this chemical law. So we can now plot the cosmic star formation history by integrating this luminosity function. The result is here. So this is cosmic star formation history or infrared luminosity, all plotted by Akari. So these high redshift points are from Akari's NABT field, and this low redshift point is from Akari's all-sky survey. Then especially this low redshift point, there's no all-sky 5 surveys planned in the future, so I hope it will stay the best value for decades, probably. And then lastly, I want to mention a little bit about future of the NAB field. So I mentioned at the beginning, Akari did this kind of observation, all-sky survey, and then deep field here. The reason we have deep field at NAB is we have a good visibility from Akari's orbit. And then this is more or less same for the many future space telescopes. Because for space telescope, the enemy is the sun and then the Earth, right? Space telescope never want to observe sun or the Earth, right? So then naturally this NAB region and SCP region have a good visibility, so it's good for long exposure deep field. And then actually if you look at some future telescopes, many of them have NAB deep field. So you already decided to do a deep field in NAB. JWST has deep field in NAB, and I lost EROGITA also have a deep field. EROGITA has the similar orbit as Akari, so has a deep field in NAB. Then, yeah, so, okay. Then, do you know how many papers are published in Cosmos field? So right now, a lot of galaxy evolution studies are coming out from Cosmos data, right? Do you know? Wait, how do you know? As I looked at yesterday, it's more than 1,070 that's ADS that found. But the NAB, because all these future telescopes are having deep field there, it's going to be a next generation Cosmos field. And then it's much larger, 10 square degrees. And then we can read this activity, we can read this field because we already have Akari's data, and then we also, for Akari's data, we also took deep HSC data, and then we are also trying to take PFS data here. One of the things we're doing is, so this is again Dave Sanders, University of Hawaii, and we are trying to observe much wider field with Subaru's HSC to take deep optical data. Yes, you're here, but I cut you. And then also, once Subaru's prime focus spectrograph started working, we want to do a spectroscopic survey here. And then all of the weakness we currently have, such as listed here, will be removed. And then we can do true sensors of obscure star formation and then obscured black holes. And again, we can lead this activity because we have already have initiative data. One example, I show you one example. So JWST is just a copy of Akari, just it's 10 times larger. If you look at compare the filters, so these are Akari's 9-band mid-infrared filters, and this is JWST Miri's filters, and it's very similar, right? So I'm training my students with Akari data now, but once JWST data comes out, And then, for example, in this example, my students are trying to separate AGN and star-forming galaxies using mid-infrared wavelengths. I think Tina talked about this this morning. Advantage is here is this is using infrared, so it's free from extinction problem. And then now she has a code to do this as it fitting for the mid-infrared data. So once JWST data are available, we can jump onto the data and then quickly write a paper based on the JWST. That's what we are trying to do. Okay. Then, okay, I wrap up here. So I talked about two surveys, the NMP deep field. We took advantage of 9 mid-infrared filters with new HSC deep data. We constructed minimal luminosity function in this range. And then using Akari's all-sky survey, we did the most accurate local infrared luminosity function in this paper. Okay. And then in the future, we continue this work in the NMP field taking advantage of future satellites. I stop here. Thank you, organizers. Thank you, everyone.
Okay. Great stuff, Tomo. You made me miss Dave so much. Sanders. So I guess 2 questions. The first one is you got 5 square degree, right? And how many sources do you have for
it depends on
the deep field?
It depends on the band, but Akari sources are about 90,000 infrared galaxies.
So there must be efforts on trying to measure the 2-point autocorrelation function, right? Try to constrain the halo mass.
That's possible, I think.
Right, because you're probing the redshift range that currently is missed. There's a gap on halo mass measurement between redshift 0 and redshift 1-ish. And 1 to 3 we can constrain it with dusty galaxies, SMGs, but there's a gap between 0 and 1. And it seems like your sample fits into that gap really well. So spatial clustering measurements will be pretty cool.
You're welcome to work on it.
That'd be great. Let's collaborate. The second one is the local luminosity function. Now you have very precise measurements. Is there any model predictions that can test on?
Well, I'm an observer, so I'm trying to present the best observational values.
Okay. All right. Any theorists in the audience that have good model for it? I guess not. All right. Something to work on. Thank you.
Very deep point in your rate 1, in your luminosity function.
That's the point. I'm not sure about that one.
What is that? You don't know?
I don't know about that one.
Okay.
You're talking about the next one.
Yeah,
this one, right?
yeah, the low one, the bottom line. The third one, the third rate.
This one, right? You're talking about, right?
The third rate.
No. Our one is black one.
But that is also your work, photo.
I don't know this guy. Who is this guy? That was wrong, I think. Our values are correct. Who is this guy?
Okay.
Well, this is old work, so.
Okay. One more questions? Okay, our final question. Annie.
I have a question on your second page.
Second page. Second page, you mean numbering?
Yes.
You mean this?
No. There is a page which shows number of dumpling. The rest of it.
Which one? Sorry. I need to slide. This one? This is my
Is
second
it
slide.
second? Maybe third?
Third one? This one?
You have one show numbers of the dumpling Okay, maybe not. Yeah, this
Yeah.
one. Yeah, my question is, are you going, because you show it's published in 2019, right? So which journal published this number?
This is Google. Lyman Page is a Google founder. So I searched Google, so I just quoted his name here.
So this person he published a paper to show
sorry.
the number of dumpling restaurants in Taipei.
Sorry, this is Larry Page, the Google's founder. So I just put his name here. There's not much meaning here.
Okay, so let's thank all speakers
Thank you
this
very much.
morning.